Hi everyone, let's take a look at the related rates section, section 3.1. There's really not enough word problems assigned and achieved for my liking in this section, but we'll make the best of the few problems, well, the 14 problems that are assigned. This first question's almost so simplistic, it's difficult. So it says here, John's bathtub is rectangular and its base is 14 square feet. How fast is the water level rising if John is filling the tub at a rate of 0.5 cubic feet per minute? And we're supposed to use decimal notation, giving answer to 3 decimal places. Okay, so here's what I did for this problem. I went in and I said, I have my volume formula, and it's going to be with respect to y. I let y be the height of the water in the bathtub. Now, we know that the volume of any rectangular solid is length times width times height, which is the same thing as the area of the base times the height. Well, we're given the area of the base. So instead of doing the length times the width, we know that that is a constant 14 area base. Now, the volume is just going to be whatever that area of the base is times the height. So the volume with respect to y, the height, is just 14y. So then if I say, okay, take the derivative of this expression with respect to time, the derivative of the volume with respect to time is simply dv dt. The derivative of 14y with respect to time is going to be 14 dy dt. Now, using the information that I was given in the problem, and you've got to be able to take the rates and understand what they represent, it says that the water level is how fast is the water level rising? So my goal is to find dy dt if the tub was filling at a rate of 0.5 cubic feet per minute. Well, that's the change in volume with respect to time. So I'm given dv dt is 0.5. I'm supposed to find dy dt. So it's just plugging into this equation. I know that the change in volume with respect to time is 0.5. That's going to equal 14 times dy dt. Thus, dy dt is going to be 0.5 divided by 14, which I went ahead and reduced to the fraction 1 over 28. No need to do that, though, because they just want a decimal answer. Whether you do 0.5 over 14 or 1 over 28 as a decimal, that's 0.036 feet per minute. And you can see that that's precisely what I entered in to achieve, and achieved, liked it. For the next question here, let me move this up out of the way. So this one had part A and part B. I'll just look at part A for now. It says the radius of a circular oil slick expands at a rate of 4 meters per minute. We're supposed to find how fast is the area of the oil slick increasing when the radius is 50 meters. Okay, so I know that the change in the radius with respect to time is going to be, it's changing at a rate of 4 meters per minute. I just go ahead and use 4 for my formulas. Now, I'm told that the radius is 58 in this problem. So my area formula, it's just area of a circle, pi r squared. I can take the derivative of that with respect to time. Derivative of a with respect to t, dA dt. On the right-hand side, the 2 would come down in front, and then I would have 2 pi r to the first times the derivative of r, which is dr dt. So now I can say, all right, this is my area formula. What do I know? I know I'm trying to find the rate of change of the area, and I know how fast the radius is increasing, and I know that at the point of which I'm interested in the radius size. So I can say, well, dA dt is going to equal 2 pi times the size of the radius at the point of interest, 58 meters, times the rate of change of that radius with respect to time. It's increasing at a rate of 4 meters per minute. So then I can just plug this all in, and you can see I had 464 pi, and that would be in square meters per minute. No reason to put it on our paper because it's automatically already put on achieve at the end. So I have 464 pi square meters per minute. Now, part B in this problem, I'll move this up and move this down. It says, if the radius is 0 at time 0, how fast is the area increasing after 4 minutes? Well, okay, they just want you to do a little bit of extra work here. Instead of telling you explicitly how large the radius is at the time of interest, they give you the initial size of the radius, 0 in this case, and then they give you a time that they're interested in. So we want to know how fast the area is increasing after 4 minutes. But they only tell us that the radius is 0 when t is 0. But I know from the original problem that the radius is growing at a rate of 4 meters per minute. So I simply just say, well, if r is 0 when t is 0, then at 4 minutes, r is going to be the initial amount plus the time elapsed times the rate of growth. Well, the time elapsed and the rate of growth happen to be the same thing in my problem. So you can see the radius at the point of interest is just 16 meters because it's been growing at a rate of 4 meters per minute for 4 minutes. So I can say, okay, the radius at the point of interest is 16 meters. Now I plug that back into the exact same formula that I had before. This is the only difference now is my radial length. It's 16 instead of 58. When I multiply that through, I'll get my 128 there. Let's see if I can make that a little more clear. There we go. And you can see on achieve, I put the 128 pi and achieve liked it. For the next question here, we have, it says, assume that the radius r of a sphere is expanding at a rate of 90 centimeters per minute. The volume of the sphere, V, is equal to 4/3 pi r cubed, and its surface area is 4 pi r squared. Determine the rate at which the volume is changing with respect to time when r is equal to 15. Now, please notice it's giving you more information than you need. In the problem, it's explicitly asking us to determine the rate of change of volume. So do I need the surface area formula? No, that's extra information that's unnecessary for this problem. So I can say I need the volume formula, and I'm trying to find out how fast the volume is changing. So I take that volume formula, I take the derivative with respect to time. The left-hand side is going to be dv dt. The right-hand side, the 3 is going to come down, multiply the 4/3 and give me 4 pi r to the second times the derivative of r, which is dr dt with respect to time. So now I can say, all right, I'm trying to find the change in volume. What do I know? Well, I know how large the radius is at the point of interest. I know the rate of change of the radius at the point of interest. So I just plug everything in. 4 pi times r, which the problem said was 15. Of course, that's squared, times dr dt, which the problem said was 90. So I'll plug that in and I'll get 81,000 pi. And you can see the units are already included, so I just didn't bother putting them on my paper when it's on the achieve already. So 81,000 pi cubic centimeters per minute is the rate of change of the volume with respect to time. Now, if I look at number 4 here, this one, it looks at the other part of this problem. It almost looks like the same problem. It's still giving you a volume formula. It's still giving you a surface area formula. We're told that the radius is expanding at a rate of 70 centimeters per minute here, and we're interested in the time at which the radius is equal to 40 centimeters. Okay, but now please notice it's asking us to determine the rate at which the surface area is changing. So that volume formula up here, completely unnecessary this time. So I look at the area formula, and I know surface area is going to equal 4 pi r squared. I take the derivative with respect to time. I get dA dt is going to equal, 2 comes down, multiplies the 4. I get 8 pi r to the first times the derivative of r, dr dt. Now I can say, okay, I'm trying to find this dA dt. Plug everything else in then. We know r is 40 at the point of interest. We know dr dt, it's expanding at a rate of 70 centimeters per minute. So I just plug in the 40, I plug in the 70, multiply across, and I'll get 22,400 pi. And this would be in square centimeters per minute. Again, the units are already accounted for on achieve. For the next question here, it's, again, very similar. It's saying to assume that the radius of a sphere is expanding at a rate of 10 centimeters per minute. And we know that the volume of the sphere is 4/3 pi r cubed, and the surface area is 4 pi r squared. We're supposed to determine the rate at which the surface area is changing. Now, the thing that makes this one a little bit more difficult is it doesn't give me the r value at the point of interest. Instead, it tells me that I'm wanting to find the rate of change of the surface area when time is equal to 2 minutes. Now, we're told that we can assume that the radius was 10 at t equals 0. So I just go in here and I reason that, well, if the radius was 10 at t equals 0, then the radius at the point of interest is going to be that initial radius at 0, the 10 centimeters in this case, but then it's growing at a rate of 10 centimeters per minute. And I want 2 minutes later. So then I can say, well, then easily my radius is going to be the initial radius plus the rate of change of the growth of the radius times time. So I can say, well, that's going to be 10 plus it's grown 20 centimeters in the 2 minutes time. It's going to be 30 centimeters at 2 minutes. Now I plug this into my area function. I can say, well, all right, well, actually, before I plug it into my area function, I have to take the derivative because I'm not trying to find the area at the point of interest. I'm trying to find the rate of change of the area. So I can say, well, dA dt is equal to 8 pi r dr dt, and then plug in what we know now. That's going to be 8 times pi. We know r at the point of interest was our 30. And we know that the rate of change of r is growing at a rate of 10 centimeters per minute. So we put that in. Multiply across, this is 300 times 8, 2400 pi. And you can say that's going to be the rate of change of square centimeters per minute. So the area is growing by 2400 pi square centimeters per minute. And you can see that that's precisely what I entered in on Achieve for this problem. For number 6, see if I can move this up and show it on the same screen. There we go. Yeah. So now it's giving me this drawing and it's saying, consider a ladder sliding down the wall as in the figure. The variable A is the length of the ladder. So we know that's not going to change. The length of the ladder as it's sliding down the wall is going to remain constant. The variable H is the height of the ladder up the wall, and X is the distance from the wall to the ladder's bottom. Okay, now in my problem, it's saying, suppose that the length of the ladder is 6.9 meters. So you'll see on my little triangle down here, I labeled A 6.9. And the top is sliding down the wall at a rate of 1.2 meters per second. So, and it said in the next line that H is equal to 1.9. So I labeled H 1.9. Now, if that ladder is sliding down the wall at a rate of 1.2 meters per second, it's extremely important that you're able to understand, oh, then that means that the change in H with respect to time is negative 1.2 meters per second. It starts off at 1.9 meters per second in this problem, but we know it's moving down the wall. So please don't put that as 1.2 here. It's going to cause you to get it wrong. You need to understand it's negative because H is decreasing in length. So now I'll say, okay, my goal is to find out, calculate dx dt. That's going to be how fast this base is moving away from the wall. And I already know dx dt is positive. As the ladder falls down the wall, its base is going to move away and increase in length. So the first thing I did here was go ahead and find out the length of x. I'll have to know that. And easy Pythagorean theorem, I can say x squared plus h squared is equal to a squared. You'll see I went ahead and plugged in my numbers over here. X squared plus 1.9 squared is equal to 6.9 squared. That gave me x is equal to the square root of 6.9 squared minus 1.9 squared, which ended up being the square root of 44. It's probably best that you just keep it exact like that. Now I said, okay, I know x is the square root of 44. How about I use that exact same formula, the Pythagorean theorem, to get all of my variables in this equation and then be able to take the derivative to understand what the rates of change are. So I plug in my equation, the derivative of the left-hand side. Now, please remember, whenever you're taking these derivatives, anything that varies must have a variable and it must have a derivative rate of change. If it's constant, we know the derivative of any constant is 0. So when I go into the left-hand side, you can say, well, derivative of x squared is going to be 2x times dx dt. I need that. The derivative of h, 2h dh dt. I need that. But on the right-hand side, now, what if a student said, well, I'm going to call that 2a times dA dt? Technically, it's not wrong, but it's not helpful. And you think, well, why is it not helpful? Because think about this. What is dA dt? The rate of change of the length of the ladder with respect to time. That ladder is not changing length with respect to time. So it's better you just think of it, oh, it's a constant length. Derivative of any constant is 0. Or you can alternatively say dA dt, it's not changing in length, it's 0. So 2a dA dt, all of that's just 0. Now, I go ahead and solve out, and I can say, well, once I put the 0 over here, then I can say, well, how about I go ahead and divide both sides by 2? So I did that. Once I divided both sides by 2, I moved the h dH dt to the right side. It became negative. Now, I need to solve for dx dt. So I can say, well, dx dt is everything I have over here divided by x. So please notice, negative h, well, that's my negative 1.9. Now, why didn't I put a negative there? Because I knew I had a negative times a negative. So I just went ahead and kept it as a positive. So I have 1.9 times dH dt, 1.2. A negative times a negative is a positive, divided by the square root of 44, since x is the square root of 44. And that gave me a 0.344, which now you can see achieve loved that answer. Now, up next, we are looking at number 7. Let me make this a little bigger to where you can see my work now. Number 7, similar. It says a 6-meter ladder is leaning against a wall. The bottom of the ladder is 1 meter from the wall at time t equals 0 and slides away from the wall at a rate of 0.4 meter per second. So you can see I did not label x as 1 meter. That's because that's not the length of x at the point of interest. So it says to find the velocity of the top of the ladder at time t equal 2 and take any upwards direction as positive. Well, I automatically know if the ladder is sliding away from the wall and it's also sliding down the wall, dy dt is going to be negative in this problem. It's not going to be positive. Up would be positive, down is going to be negative. So, okay, now I'm supposed to find dy dt when t equals 2, and I'm given that the rate of change of x with respect to time is 0.4, and that the initial size of x is 1. That's what it says in that second sentence. The bottom of the ladder is 1 meter from the wall at t equals 0. But I don't want to know the rates of change at t equals 0. I want to know the rates of change at t equals 2. So that's what I put here in this next line. I have to find x at the point of interest. X is going to be the initial size plus the time that has elapsed, 2 seconds, times the rate. It's increasing at a rate of 0.4 meters per second. So you can say, well, that's going to be 1 plus 2 times 0.4. That's going to be 1.8. That's where that horizontal distance came from there. Now I can say, well, okay, I can easily find the vertical distance at the point of interest then, because I know that Pythagorean theorem, x squared plus y squared is going to equal 6 squared. 1.8 squared plus y squared is equal to 36. So I went ahead and solved that out. Y is going to equal the square root of 36 minus 1.8 squared, gave me the square root of 32.76. Now, I just left it as that. Again, it's better if you get exact values in there rather than whatever that's equal to in a long decimal form. So I'll say, okay, this is going to be helpful in the future. Now, I go back to that same Pythagorean theorem. anything that's a variable must be a variable before you take the derivative. So please don't put a 1.8 squared over here, or else you'll think, oh, well, the derivative of that is 0. Anything that varies must have a variable and it must have a derivative. So I can say, okay, the sides are variables, but the length of the ladder is a constant. So I'll just say, well, 6 over there. So x squared plus y squared is equal to 6 squared. Now I take the derivative. 2x dx dt plus 2y dy dt is equal to the derivative of any constant, 0. Now my goal is to solve for dy dt. So you'll notice I went ahead and plugged in everything I knew. Oh, and before I talk about plugging things in, what I will always do from this step to this step, I will always go ahead and divide by 2 on each side. There's no reason not to. So I just went ahead and divided 2 on each side. Of course, 0 divided by 2 is still 0. Now, if you ignore the 2's, you can say, well, your x term, we know x is 1.8, dx dt is 0.4, plus the y term, square root of 32.76 times dy dt equals 0. Now I can easily say, well, then dy dt is going to equal, these two move over first and become a negative product, divided by the coefficient of dy dt, the square root of 32.76. And when I do that, I get that the y value, the height is moving down the wall at a rate of 0.126 meters per second. Now, if we did write out a sentence answer, you wouldn't say negative if you said down. That's a mathematical double negative. So if I wrote out a sentence answer, I would say the ladder is moving down the wall at a rate of 0.126 meters per second. But if you're just putting an answer in isolation, not in a sentence, then you just say, well, the rate of change of y with respect to time is the negative 0.126. And that implies to the viewer that, yeah, it's moving down the wall. And we see that that's the same answer that Achieve had for that one. Next question here. Number 8. It says to suppose that both the radius and height of a circular cone are increasing at a rate of 2 centimeters per second. So you'll see that's the first thing I did. Given that dr dt is equal to dh dt, the radius and height of the cone are both increasing by 2 centimeters per second. Okay, now, second sentence. How fast is the volume of the cone increasing when the radius is 10 and the height is 20? So I went ahead, put in my other information, height 20, radius 10. Well, the volume of a circular cone, the basic formula, is 1/3 pi r squared h. Now I need to take the derivative of this formula with respect to time. So I can say, all right, the derivative of the left, dv dt. The derivative of the right, you need to be a little careful with because you have two differentiable functions with respect to time. The radius is a variable with respect to time and the height is a variable with respect to time. So you have to use the product rule. So I said, well, the derivative of the first, 2 came down, multiplied the 1/3, I get 2/3 pi r to the first times the derivative of r with respect to time, all times the second, h. And then plus the first 1/3 pi r squared times the derivative of the second, which is just your dh dt. Now I can say, okay, the derivative has been taken successfully. Can I plug values in? I should be able to. So I know that r is equal to 10, dr dt and dh dt are equal to 2. So I plug in the 10, I plug in the 2. I know h at the point of interest is 20. Plus over here, I have 1/3 pi r squared, that becomes 10 squared, times dh dt. Again, that's your 2 centimeters per second. Whenever you're evaluating this, that first one becomes 400 times 2, that's 800 pi over 3. Your second one's just 2 times 100 times 1/3, that's 200 pi over 3. But it wanted a decimal answer to 1 decimal place, so I just went ahead and put this into my calculator. 1,000 pi divided by 3 simplified to 1,047.2. And again, I didn't put units because the units are accounted for here. That's in cubic centimeters per minute. Okay, guys, now I'm going to stop this video at this point and I'll do the remaining problems, just 9 through 14, in a separate video.